Okay, today we will start with the transistor. Okay, the first thing we'll be talking about DC or transistor, and as you saw, this is a symbol for the transistor. We have a few different transistors. One will be NPN transistor, and the other one will be PNP transistor. Both things, we'll see what the difference. Okay, transistor, they can get a base, collector, and emitter. That will be the same for both transistors. Okay, that should be the base, emitter, and the collector. Okay, now see what the difference. You see at the NPN emitter, get the arrow coming out right here, and the PNP, the arrow from emitter coming in. Okay, so you can see at the base current IB, the base current coming in, current IC, collector current coming in, and emitter leaving. However, on the PNP, IB coming out, IC coming out, and IE coming in. Okay, and this is a basic formula for either NPN or PNP. IE equal IC plus IB. Okay, in the case IB is too small, so IC almost equal IE. And the other thing we have to know, that is the current gain, beta, by definition, equal IC over IB. And alpha, okay, will be equal IC divided to IE. Normally, we're using beta. That's the ratio between IC and IB. Okay, that's a very basic thing we have to know. Okay? Now, we're talking about physical for transistor. And you know the diode already. The diode, you can see they're using the PN junction, okay, to make the diode. That will be A and C, okay? and that will be VD V minus VC. Okay, and last time we already see that the P side and side. P side contains the positive pole, and side contains negative, okay, electron. Okay, so when the P side higher than N side, 0.6, 0.7 volt, and the electron from N side to the P side, okay, will be moving. So that's why you get the current. So let's see. It will be a P side. That will be a N side. Okay. It will be point A, and that will be point C. Okay. So that's what we call VD equals V A C E V A minus VC. Okay. So we already know when VD equal or higher than 0.64. Okay. Then the current will be flowing from A to D. Okay. Then when they get the two diode combined, make it to be a transistor. First thing, we see NPN. So that will be N side, P side, okay, P side, N side. Okay. They make up the NPN. For P and P, then this will be the P side. Okay. And this is N side here, P and P. Okay. So when this diode get more voltage higher than 0.6 volts, so the electron from N side move to the P side. Okay, that's NPN. Okay, and now you see the symbol here, PNP, and that will be NPN. So when the voltage high VB, okay, higher than 0.7 volt, the thing is you can see right here at this point, V, V, E, just a diode. So it will be equal 0.7 volt. So if V be higher than 0.7 volt, so the diode here will be conducting, allow the current flowing, okay, from B to A. So when you're looking into the transistor, you must know is it an NPN or PNP. Okay. Normally, when you're working on the level, the current they draw opposite instead go into it. They opposite going out to the current. The thing is, 11 volt, they using the draw current by electron moving. Okay? You understand? We get the current based on electron moving. However, we're using the conventional current. Okay? That means opposite to the electron moving. Okay? So that's why in the lecture here, you can see the current moving from B to E. However, in that one, they can draw opposite. So don't worry about that. We're using conventional current. Okay? And this is a real op amp. No, sorry, transistor. Okay? This will be NPN and this will be PNP. If you're working on the left phone, you have to use this or the other one. Okay? Transistor. And now you can see, you can get the bay here, F meter here, collector here. That means from the bay to collector, you get a diode. And the bay to F meter, you get another diode. Okay? And that diode will be this way. However, PNP, they get diode will be opposite. Okay? Now, when you're looking into this circuitry, you can say this is an NPN. Okay? NPN. So, this is RB, the base resistor. And this is the voltage applied. Okay? And this also the voltage applied using for transistor. So first thing you can see the current flow here, IB. And we already know VBE here, positive, negative, 0.7 volt. If the VB, okay, you know that will be the base collector at meter. If voltage VB here higher than 0.7, then the transistor will be on. Okay, you get ID, base current, IC, collector current, IE. Okay, it's the ammeter current. And you already know we get the formula beta IC over IB. And also you can get IE equal IB plus IC. Okay. Now, in this example here, they given you beta. They want to calculate that beta DC. Okay. And IE. They given to you IB equal 50 microamp and IC equal 3.65 milliamp. Okay, so now they want to calculate the beta. Can you do it for me? If you're doing it right, the answer will be beta equal 73 and IE equal 3.7 milliamp. Okay, you can try. That is not hard to do it. Okay, let me know if you get the right answer. Okay, now the circuitry again. NPN. This is the base collector admitter. Remember, from the base to the admitter, VBE for silicon diode, the voltage will be 0.7 volt. That's only telling you if the input applied higher than 0.7, then the transistor will be on. Let the current flowing from the base to the admitter. Okay? So, first thing, they've given to you the formula here. IB equal VBB minus VBE divided URB. That's easy to calculate the current. Okay? So, if you get the current IB, you can calculate the current IC. Okay? Now, you know IC, okay, equal beta IB. Okay? And if you want to calculate IE, even IE, okay, equal IE equal IB plus IC. However, they wonder using the same way calculate IE, but they using different formula. IE right here. I1 plus beta. Time IB. And if you want IC, beta time IB. Okay, so basically, that's just a circuitry they give you on of the basic calculation. Okay, you want to calculate the ID, or you want to calculate the VRC. VRC. Okay, that means the concept here. If you get IC, you times RC, you get VRC. Okay, and VCA, that means VC minus VE. Okay, that's a VCA. Okay, so that's just given you basic, the formula using for the transistor, even NPN or PNP. The difference will be the current flowing will be different. Okay, for formula will be the same. Now, try to see for the very basic circuit. Okay, they want to calculate the VBE, IB, IC, IE, everything in the circuit shown. However, they given to you beta equal 100 and VBA 0.7. Okay, so the first thing you know, that's right here, plus minus 0.74. So you already say VBA, they will be 0.7. That's a given, so you don't have to calculate it. Okay, and now they want to calculate the current IB. And you already know IB equal VBB minus VBE divide RB. Okay, so you can calculate that IB. IC equal beta times IB. IE, we prefer to using this formula. IE equal 1 plus beta times IB. Okay. And now VB. That means VB equal. That means from the base to the ground, only 0.7 volt. Okay. VE 0. E connect to the ground. VC right here. Okay. VC. Let's see. How can we calculate the VC? You know the VC. This what you get the VCC. So in order to get the VC, then let's see. Equal V C C minus voltage drop RC minus V C or VCC minus IC half RC. Okay? And now they want the VCE. That means the voltage here. VCE. VC minus VE. Okay? VE equals 0. Okay? So you have to do a calculation to get a law. Okay? Now, for the transistor, the region of operation, okay, the first one, cut off, yield in switching application. That means turn on, turn off. Active, yield for linear amplification, amplifier. Saturation, yield in switching. That means the same thing. Like cut off, okay, switching application, breakdown, can destroy the transistor, okay? Now, cut off, diode from B to S meter is off. That means no current flowing, okay? Active, okay? Diode from the bay to S meter is on, and the diode from the bay to collector is off. Saturation, both diodes are on, and V from collector to S meter, VCE almost equal 0. So at least you have to know, okay, the operation region using the transistor. Either they cut off or they saturation. You understand, cut off that means no current flow. Okay? Active. That means you get a current flowing. They using for amplifier. Okay? Saturation, same thing. Using for switching. Just turn it on or off. Okay? Breakdown, that means high current of voltage will be destroyed. The transistor. Now, this is an example. You see the transistor NPN. Okay. First thing, you up get the VE. Okay. And the first thing they say VE equals 0. What they want to do for transistor circuit show what VCE. That's what they're asking of VCE here. Now, in case V in 0, that means no current flow, IB equals 0. So the transistor will be off. Okay, now you can see this is the current IC. This is the current IE. And the current IB. So if V in equals 0, IB equals 0. So I see same thing. The transistor will be open. Okay, i.e. same thing. So the solution here, when V in equals 0, transistor is off. IB equals IC equals IE equals 0. They open. Okay, therefore VC right here. Okay, what VC equal? The thing is, you understand if we get a VC, okay, VCC on this side, 10 volt, and VCE will be here. So when you get an open, okay, open right here, so the voltage 10 volt here, same thing, the voltage FVC, okay, that's why they say VC equal VCC equal 10 volt. Voltage drop across RC equals 0. Okay, they're telling you when they get open FVC, no current flow. So the voltage this side or the voltage the other side will be the same. Okay. Number 2, what minimum value of IB is required to saturate this transistor if beta equals 200. What minimum value of IB is required to saturate this transistor? Now see what they try to explain to you. Since transistor is saturated if VCE almost equals 0, then you get the IC now will be IC saturated. Okay? That means they say the VCE here equals 0. So VC 0, you get 10 volt VCC. You can calculate the IC. Okay? 10 volt divide IC. Here. VCC divide IC. You get 10 milliamp. However, this current is I saturation. Okay? Therefore, IB, calculate IB equal IC divide beta. So that's why you can get IB. Okay? Number C, calculate the maximum value of RB when V in equal 5 volt. So now if you get a 5 volt here, okay, when the transistor is on, voltage across RB is VRB. That means the voltage across resistor RB equal V in minus 0.7 divide RB. Okay? When the transistor is on, voltage across RB equal VRB equal VE 5 volt minus VBA 0.7 volt. You get 4.3 volt. Then LB mic equal VRB divide to IB. Okay? VRB equal 4.3 divide to IB minimum here. Okay, not 50 microamp given you the value of RB equal 86 kilo ohm. Okay, if you get any question, you get up. Okay, I will try to help you. You have to be understand. Okay, in order you can do later. Now, for this one, they call the set of curve is also called a family curve. Now, you see this is a transistor NPN. This stands for the current IC. Okay? That's the IC. Okay? This is the voltage VCE. That's the VCE. Now, you can see this is drawing here. What is it? This will be using for IB. Okay? That current IB. So I given you example. If I get the point in here, so I know current IB equal 40 microamp. And if you want the current IC, you go into the left. Okay? You get the current IC. If you going down, you get a VCE. Okay? Now, in this display, the area here that's what they call saturation. Okay? And any point in this area That means active using for amplifier. Okay. And the last part here, that's what they call a cut off. We already know. We get a cut off region or saturation or active. Okay. That's using for engineer when they try to design the transistor. Okay. What that means? If I try to design a transistor, I can pick the point in here. Okay. At this point, I can get the current here. I get the VCE here. And I can get the saturation current here. The thing is you want the amplifier and transistor must be in active region. The thing is saturation region. That means no voltage gate. Okay? They're using for switching or cut off region. Okay? Cut off region here. The transistor will be using the same for switching, turn it on, turn it off, not amplifier. So we pick the point here, you can get the current IB, you can get the VCE, we can get the current IC. So that will be given to you the choice to get the resistor connecting to the circuitry. Make sure transistor will be active. Okay? Even the temperature can go up or down. This one can move either up or either down, but they cannot be saturated. They cannot be cut off. If you pick a point at this point flowing here, not good. Why? When temperature changes, then this Q point here, they can move to the saturation. They no longer to be amplified. Okay? Or you pick the point at this area. They can be go to cut off if they don't want it. When they design amplifier, guarantee they will be amplified no matter what. So that's why they can pick the point, okay, in the middle here. Okay. This only helps for you guys when you're looking into this one. You can understand, okay, each region. Now, next, they want to help you. How do we draw? How do we draw the load line? Okay, that means the line here. That's what we call a load line. And that, if you design amplify, you pick this one. That's okay. Or this one, okay. Or this one, okay. But we don't want this one close to the cutoff or the close to saturation. They can be no longer amplified. So now how to draw? Here. First thing we need to draw point A. Point A, at saturation, I saturation equal VCC divide RC. They will be a 10 volt divide 1K. Okay, that's RC right here. So you get 10 milliamp. Okay, so this one, I saturation will be 10 milliamp. and point B here. Point B at cutoff VCE equal VCC. Okay, and VCC is 10 volt. So that's why that will be a 10 volt. And you draw the line. That's how you get the load line. Okay, that's for designer. Okay, if you want it, you can pick the kill point here or here or here. That be fine. Okay, cannot be close to saturation or close to the cutoff. They will be no longer amplified if temperature changing. Okay, this circuitry, let's see. NPN, VBB value, VCC value. Okay, nothing to talking about that one. Okay, that just telling you. Okay, this is a IC versus VCE for one value of IB. Okay, and another one, family of IC versus VCE third for several values of IB. Only the difference is they using only one IB. This one, they can be using either one. You can select which one. Now, this is a cutoff. Okay, that means input 0. So that's why transistor cutoff open. And that's only telling you from the collector to the F meter, they open switch. You see that? And another one, saturation. Okay. Granted saturation. Okay. So basically, VCE equals 0. That's a VCE right here. That's a C. That's a E. So VCE 0, that means C and E the same. That's why this will be using for close switch. That is why you can see in your home. Okay, you turn on, okay, or you turn off the power. Okay, that means when you turn it on, they're using the open switch between collector and meter. However, when you want to connect, you put it out. Then we will go to the close switch. They connect collector to F meter. Okay, for the circuit code, fine. IBICIE. Okay, we already know. First thing you need to calculate the IB. This is the formula. VBB minus VBE. Okay, divide RB. You get IB. Okay. And if you want to calculate the IC, beta IB, beta is given you here. Okay. And you calculate the IE and VE, VB, VC, VCE. Okay. Okay, right now, I can stop it here right now. Let's see. I see. I want to hey, so that's what we think I can. We don't have any problem to do it. For example, number 3, okay? You let the guy do it. And this is a solution. So make sure if you can do it, okay? And another problem, okay? And they want to calculate IBS, VBA, okay? And I get the answer for you. I let you do it. So, example number 4, they tell me the key point for the circuit. So, leave it beta equal 200. That means you need to calculate IB. Okay, let's see. IB, easy. Okay, VBB minus 0.7 divide IB. IC equal IB times beta equal 200. IE equal 1 plus beta times IB. VCE will be equal VC minus VE. Okay? And draw the VC load line. To draw the load line, we need to know the point A. Okay? The point A and the point B. We know the point B will be equal to VCE. That's transistor in saturation. And now, point A, you need the current IC. Okay? How do we calculate the current IC in saturation? And go back here. Here. At point A, saturation, high saturation, VCC, divide RC. Okay? So that will be help you to get point A and point C and draw the line. Okay? Okay, so there's a solution for that example. Okay, try to read it. F meter buyer. Okay, That's just given you. Same thing, just formula. That need a feedback bias. That means different way to connect the circuit. Okay, by bias. Okay, the least predictable different move with replacement, different move with temperature, not particle. Collect the feedback better than admit feedback. Bias, different still move. Limit for application. Okay, to supply admitter bias. So you get one power supply and another power supply. Okay, that requires two power supplies. So no one you want to do it. Okay, that's just a calculate for using two power supply. Okay, not practical. Now, this is a voltage divider. We will be using on the path. Normally, if using two power supply, that's not a good way to do. So that's why they using two resistor R1 and R2. Okay, so we'll see how they work. First thing to calculate the VB. Right here, VB. So this is just a voltage divider. Take a VCC times R2 divide R1 plus R2. You get VB. Okay? If you get a VB, and basically, you know VB is here. Zero point seven. So you can calculate the VE. VE equal VBB minus 0.7. Yeah. Okay. And after you get the VE, you can calculate the current IE. Okay. IE here. Okay. This is IC. And this is IB. Okay. Then you can calculate the IE. VE divide, okay, RE. That's a mistake here. Okay. And ID equal IE divide beta plus 1. Okay. R1, R2 form a voltage divider. Okay. IC equal beta by B. V RC That means the voltage okay equal IC RC. Okay, and now if you want to get the VC, take VCC minus the voltage drop across RC, you can get VC. Okay, VC equals VCC minus IC RC. Now, voltage divider DC higher. Okay, we'll know. If you want to calculate VBB, that means the voltage here. That is VCC times R2 divided by 1 plus R2. IB is not born enough. You need to compare to I2. Therefore, more detailed calculation need are in base VBB divide IB, where R in base resistance from BB to RA. Okay, so if you're looking into the transistor input, okay, so that's why they go up. RE, okay, VDB equal VDE plus IE and RE. Assume VDE less than IE and RE. Then VDB equal IE and RE. Assume IEIC beta equal beta gamma B. Then VBB beta times IB and RE. Okay, R in base, VBB, base divided IB. Total resistance from the base to the ground is R2 parallel R in base from the base to the ground. Okay, VBB equal VCC and R2 parallel R in base divide R1 plus R2 parallel R in base. Example 5. Okay, will be like, okay, example 6. Now, they want you to deal with P and P. Okay, I let you try to see how can we do. Otherwise, we'll be helping you. Okay, now they're talking about P and P. Okay, bias with negative supply. So VDD equal, you see that? They're using negative multiply. Okay? So that's why BCC thao nào chủ divide R1 plus R2. That has to be R1 and E. Okay? So you know that will be E. That will be collector. That will be the best. Okay? And that will be given to the formula. The reason is normally they're working on NPF. Okay? Sometimes PNP. But this is we asking you to get a formula to calculate what you need. Okay? That Lincoln connection. The reason they want that Lincoln connection circuitry, okay? They connect Q1. That meter go to Q2. Only thing is, Q1 they get a beta 1. And Q2 they get a beta 2. So the beta for the circuit will be beta 1 and beta 2. They want more current. That's why they connect circuitry this way. Okay? And also, you can go, you can buy the duck Lincoln transistor. They connect both inside the packet. Okay? And duck Lincoln transistor manufactured with transistor in one state. That is the one here. Okay? So whenever you have to working with a duck Lincoln connection, be careful. Okay? If you get a fault, they can do it right away. The thing is going very fast. Okay? So that's it. Any question? Anything? Okay?